Okay, I hope that you guys all brought your knives and forks because today we cook. Right? That's pretty bad. Right? Okay? Or rather, after we cook, y'all are going to eat it. No, you say eat. I don't know. We'll work it out. Anyway, here we go. Compounds. They're wildly different than the things they come from. Now, I'm going to make sure that this looks nice in my notes, and I'm just going to try to look. We've been talking about elements and their interactions. We get a new main topic today, and I think it's the last one, but there might be a couple. Okay, we're going to talk about chemical bonds. Now, remember that when we look at something like water, we have two hydrogen molecules that connect with an oxygen molecule. Now, the big question is, how do these things connect? Like, what causes that to happen? What do we call those electrons that are the outermost ones?
What's that? Valence.
Valence electrons are the outermost electrons. Now, when I talk about this stuff, I like to personify things insane. Follow up, what does that mean? Personification? Oh, my English class. Giving human-like features to something. Like, I do this a lot. I want to be really clear. Atoms, to my knowledge, don't think. I don't know that for sure, but I'm pretty confident that they do not think about stuff. Right? They don't have a brain. They're just these little balls of energy. It'd be weird if they thought, but maybe they do. I really don't know. I'm going to use the word they think, or they feel, or they want, they desire. They don't really have these emotions and things, but that's the language I'm going to use, okay? All right. Looking at it. For this, I'm going to preface this with two different types. The first kind, we are going to be real specific. We're going to define for ourselves, though, first, an ion. Okay, so at this point, we're going to hit the vocab super duper hard because I want to make sure that we all understand what we're talking about. I feel like you had a comment a second ago that I was talking and I didn't stop. Are you sure? Okay. All right, so an ion. Who has heard this word before? So eon is eon is amount of time. An ion. Okay, so check it out. If I have an atom, like, doesn't matter what it is, and I'm not going to enunciate it that hard because that feels awkward. If I have an atom, and I change the number of protons, what's changed? So you're right, let me be more specific. If you need to look at your periodic table, you can. If I have a hydrogen and I add a proton, what do I have now? Check your table. Nope, don't guess. Check your table. If I have a hydrogen atom in front of me, we'll say it's hydrogen 1, and I add to this another proton. Now there's two protons, right? And that's what you said initially, RJ, and you're right. But if I have hydrogen and I add a proton to it, it becomes what? Good. It's not hydrogen anymore. It's now helium because it has two protons. That number in the top left. Okay. If I have a proton, or if I have a hydrogen and I add a neutron to it, what does it become? So maybe hydrogen 2 or hydrogen 3, or it's probably one of those two realistically. Those are still hydrogen though, right? They're just what? With differing number of neutrons. Okay. Jade, you're going to kill the vocab quiz. I appreciate this. I'm going to ask you to just pause for a second, though. I'm going to make other people answer, too. Okay, try this again. If I have an atom and I subtract a proton from it instead of adding, it makes a new what? Not a new neutron. So let's pick one. Pick anything on the periodic table. Sulfur. So sulfur's over here. It's number 16. If I take one of these protons out of a sulfur atom, how many protons do I have?
50.
And I now have sulfur still or no?
No, it's 30.
Now I'm phosphorus. Okay, it's changed, right? Because of the number of protons. Sulfur, if we assume, just looking at it, and I'll walk you guys through this, I think that most of the sulfur that happens in the natural world has 16 neutrons and 16 protons. Can anybody tell me why I think that? I know it has 16 protons, right? It's number 16. What about the neutron part?
Because it's in row 16 and it has 16.
Love that thought, but I'm going to make the claim that selenium has way more than 16. Love the logic, though. What does the number at the very bottom of this table represent? That 32 point something? It's my average atomic mass, which we get by adding up the protons and neutrons. If I guarantee that every sulfur atom ever, because of how we say it, has 16 protons, and on average the number of protons plus neutrons is 32 point something, do you agree that average neutrons must be pretty close to 16 as well? Because 16 plus 60 makes 32. We can get all this out of the table. In either situation, let's say I added an extra neutron to a, we're talking about sulfur, right? Let's say I added sulfur and now it has an extra neutron. Is it still sulfur? You say no, careful. What do we add? I said add a neutron. Does neutron change the element that we have? Protons change the name of the element. What do neutrons change? We now have a blank of sulfur. It changes the mass, definitely. And what do you call something with a different number of neutrons but the same number of protons? It's a blank of sulfur. Starts with an I. Not yet. We haven't talked about that one yet. Isotope. Okay. The language here, it's very specific, but if we understand that isotope, differing neutrons, I'm fine with that explanation, that definition. Different number of neutrons, that's all I need. Okay, so we've already looked at two of them, right? We changed the number of protons, and we changed the element itself. We changed the number of neutrons. It's still the same element, but we now have an isotope. Okay, what haven't we changed yet that lives in an atom? We have protons, we've changed them, cool. Neutrons and electrons. So when we look at an ion, all that an ion is easy to define. It is an atom that has more or less electrons than protons. Okay. Now, I'm going to draw a picture. I don't want you guys to draw it, but I want to think about it, okay? Let's say that I'm looking at a helium isotope right now. Nature generally likes balance or likes craziness and disorder? It likes balance. If you don't believe me, grab somebody's arm that's colder or warmer than you and hold on, and over time you're going to balance out, right? Energy likes to balance, and Einstein's big contribution was everything is energy. Everything is just energy, okay. As we're looking at it, here's what I want us to consider. I have a proton, and I have a proton, and this is helium. You do not have to draw this, Fred. Okay. All right. Now, let's say, and I'll give you guys the reasoning behind some of this stuff. Here's where my electrons are going to live, in that ring, that orbital, that energy level, if you will. And if I want it to be balanced, protons have what sort of charge? Positive. So this is like +1, and now we're at +2, right? If nature wants to balance, my electrons have what sort of charge? Negative. If I want these to balance, how many electrons should this have? 2. So there's, these two cancel out, right? Those two, positive and negative. And then these two cancel out, and now we're balanced in this sense. Everybody okay with that? 2 positives and 2 negatives make balance. Cool. With that in mind, if I took one of these away, so now I have 2 protons and 1 electron. Is it balanced anymore? What is the charge of this helium atom? It's a +1, right? That's not balanced because I have a different number of electrons and protons? Check it out. What do you think we've just made? An atom that now has more or less electrons and protons. It's an ion. The other way to define this, and it's not different, it's just an alternative wording. In other words, which we'll use this IE for, an atom with a charge. Okay, if you give me an atom with a charge, it's called an ion. Now, I'm not going to quiz you guys on it, but I can either get rid of an electron, which we produce a negative, or a positive charge, I'm sorry, because I've gotten rid of one of the negatives, or I could add electrons and it becomes positive. They have different names, but they're ions all the same. Okay, beyond this, last little statement that we're going to make, and then we're going to really make sense of this. Here we go. I don't have a good rule. There is a rule, but we don't need it right now. Some atoms like to give away electrons, because they're not balanced yet. And that's the balance is a weird idea because there's several different ways you can look at it. Some atoms like to gain electrons. Okay, we're going to say that orbits, rings, or what's the last one? Electron orbit, electron ring, or electron energy levels. Okay. For this, you're just going to have to, I'm not going to quiz you on this, but I want to talk about it a little bit. Okay, atoms have stable electron orbits. Notice I'm not saying balanced, I'm saying stable, like they're nice and chill. Orbits. If there are two valence electrons or 8 valence electrons. Okay, we're not going to go into the why. This one is really rare, the 2. It's super duper rare because the only things that regularly have 2 electrons are the first 2 elements. Okay, 2 or 8. That's it. It's called the octet rule. We're not going to go into why this is the case, but 8 electrons means stable. Cool. So, as we're going through here, we are going to look at this situation, and we're going to make 2 little pictures. And I want you guys to draw this picture, okay? All right. For this, if you want colored pencils to make your notes nice, I can hook you up. Like, I have a bunch of colored pencils if anybody ever wants to use them for stuff. I'm not going to require it at all, but if you'd like them, here's a bunch of colored pencils. Don't care if you use them or not. Okay. Dinata. Cool. Here's what I want us to draw. I'm going to draw a sodium and a chlorine. Now, we're only going to draw them with the valence electrons. Okay. So check it out. I want to take a sodium atom and somebody hook it up with your periodic table in mind. Where is sodium? Na. It's the left side of your table. What's its number?
11.
Okay, so sodium is number 11. Okay. What group is it in?
3.
That's not true.
The first one.
It's in group 1? Okay, so you're probably going to see a connection here. It's in group 1, and it's number 11. So I'm going to say P plus equals 11. And I'll do it in black. It's group 1. Now, when I sketch this atom, I'm going to be honest. I'm not going to take the time to draw 11 protons. I'm not going to take the time to draw my neutrons. I'm not going to take the time to draw all the electrons. All that I'm worried about right now are the valence electrons. Okay, if it's in group 1, I want you to see if you can make the connection to how I'm doing this. In group 1, we have sodium. Now, for this case, I'm just going to say, check it out. There's my nucleus. There's all 11 of my protons. Now, for this next piece, if you wanted to, and I don't want you to draw this next part, so once we all get here, I want you to pause, and we're going to talk about one little piece. Man, chemistry is pretty cool, I think. Or terrible. Or both. I don't know. Okay, what I'm saving you guys from, don't draw this one. I'm going to add some circles. We will add something, but I'll be real specific. Okay, there's my first orbit. Here's my second orbit. Okay, because it's in period 2, right? I know that there's 2 energy levels or 2 orbits. And because it's in group 1, we're going to see what that winds up meaning as well. This first one can only hold 2 electrons. There they are. So I'm at 2 electrons now, right? And I lied. Sodium must be group 3, huh? Or period 3. Okay.
Yeah, sodium.
So check it out. My second level, and you guys do not have to draw this because we're going to have a simplified picture. My second level has 8 electrons. Okay, I've reached my stability and I'm here. I need to get one more energy level here. And how many total electrons have I drawn so far? 2 in the first, 8 in the second.
10.
I'm at 10 total, and how many should it have?
11.
11. So there's 1 out here. Okay, this is the real picture of what, it's a bad picture. It's a good, you get what I'm saying. This is a picture of sodium and a sodium atom. How many valence electrons does it have? Yep, and what is a valence electron? Because we're just going to hit this and just use the language so hardcore.
It has 1 valence.
Why do you say that? I agree.
Because the farthest.
I have, the highest energy level is 3, right? How many electrons live in that energy level?
10.
1. There's one valence electron. Now, looking at this, if you want this picture, and I've already drawn it, so I'm just going to use this one still. But if you want your own picture, bless you, here's a picture that I would suggest, bless you, that you draw. Here's my nucleus that has, I would draw this one. And then it turns out that for now at least, all that I care about is those valence ones. So here's the simplified version of it. Okay, all that you are seeing in this picture is level 3 and the nucleus. All right. I want us to construct the same thing over here. We're going to combine this with a chlorine atom. So find me chlorine on your table real quick.
Oh, chlorine. 17.
So 17 protons. And then give me a little bit more information. Can you tell me which group? Because I bet it's 17.
Yeah.
Okay, so
Fourth group.
so your groups are columns, remember?
Oh, yeah. Column.
Group 17. And rows are periods.
Yeah. Period.
Period 3. Or row 3, right? Those are interchangeable. Now, I'm going to draw the big one, just so you know. And I can do this really, I can cheat with it because I have stuff to do that. So there's my sodium. And check this out. I'm just going to copy that. We'll move it over here. And then not much has to change with mine. If I have 17 protons, how many electrons are you expecting? 17. So notice I just copied the picture for sodium, and I'll just make it into a chlorine instead. So I'll just change that little Na that I've written into a Cl. And I need 6 more electrons. You guys do not have to draw this big one. We'll draw another simplified one. So I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. Here's a chlorine atom. Okay. Are you guys okay with this so far? Okay, where did you get confused? Okay. Are you okay with finding sodium is number 11 on your table? Okay. That fact that it's number 11 means this red blob here is 11 protons. Nature likes balance. If we have 11 positive charges, or I'm thinking of it like it has plus 11 with just that, and I want it to be balanced, how many negatives should it have to counteract 11 positives? Yeah, so 11 negatives, right? So it turns out, and I'm just going a little bit further, the way that these organize is these different energy levels can only hold so many because they're only so big. The first level holds 2. I'm fine with that. Here it is. I'm full. I then move up to the next level, which will hold 8. So here's my 8. And then here's my 11th electron that has to happen to be in the 3rd energy level. Okay, I did the same thing with chlorine. Sorry, chlorine, weird. 17 protons represented right here, which is like a plus 17. For balance, I would need 17 negatives. And all I've done is I just add 17 electrons. Okay, so there's 17 little blue dots. Now, in this situation, the simplified version, and I want you guys to be really clear, make sure that this is sodium labeled somewhere here. And we're going to do the same thing with chlorine here in just a second. But here's my nucleus that has all 17 protons. How many valence electrons does this chlorine have? Which, remember, that's just the outermost. 7. Okay, so it means all I have to draw for mine then is here's my energy level, the outermost one, and 7 blue dots. 1, 2, 3, 4, 5, 6, 7. These 2 pictures are sufficient for you. I'm not going to make you draw all the little blue dots unless you really want it. Okay. The reason that I'm only looking at these outermost ones, I think will be clear here in just a second. And there's a lot of whys to this that we just can't, it's like we're in a chemistry class. The why part's a bigger question. That's always a hard thing in science. Why does this happen? That's challenging. What happens is less challenging. Okay. We said right at the beginning, and I still have it written here, I want stability in nature. Now that can come in 2 different forms. It can be charge-wise, where I want the same positive and negative, or it can be in just the electrons. I want them to be stable. Okay, right now we have everything drawn so that it's balanced charge-wise. There's no positive charge, no negative. However, turns out the electrons are more important when we talk about their stability. Right up above, we said orbits are stable if there's how many electrons or valence electrons? Atoms have stable orbits if there's 2 or 8. Now, the 2, 1 only works for the very beginning. So check this out. We want balance and stability here with these electrons. Is this one stable with 1? No, and I probably shouldn't have even said this. This one would be stable if there were 8. The 2 only works for hydrogen and helium. Okay, is this one stable?
Yes.
You say that. How many electrons are here?
Oh.
How many does it want?
8.
So is it stable?
No.
Not yet. So this is unstable, and this is unstable. Everybody agree, like when we talk about stability, the electrons, they want 8. Okay, now here's the deal. We have 2 options because these things are going to collaborate with one another. And what I mean by that is they're going to work out a way to make stability between both of them simultaneously. If these are people and they're lazy, because people are typically kind of lazy, here's the option. Either this guy just says, all right, I'll give you this one, I'm cool with that, and we do this. And it just moves. And this electron moves to here. And this one's gone. Is sodium stable now if we just take out this one?
Yes.
Okay, so I'll go back just to make sure I agree with you. You're right, just so you know. Okay, right now, I have these bigger pictures for a reason. 1 electron is not stable. It's not stable at all. 7 electrons is not stable. But they're almost stable because they want 8. Now, in this picture, it's hard to see, so I'm going to look at this picture and we'll do the same thing here. I need to do one of 2 things. I either need to add a bunch of electrons to this 3rd energy level, or there's an easier way. Instead of adding a bunch, could I just get rid of 1?
Yeah.
Now, you can't just randomly get rid of it. Somebody has to take it. But check out this awesome connection. If this one were to move over here, there would be, we'd go down in energy level, but there's how many electrons here already?
7.
1, 2, 3, 4, 5, 6, 7. That's my bad. That's a mistype. Hate that it's different color. My bad. There's supposed to be 8. I just counted wrong. Okay. If we get rid of 1 and then we move. Oh my gosh. Perfect. If I get rid of this one and I add it here instead, the highest energy level has 8 and it's stable. If I move this one to here, the highest energy level has 8 and it's stable again.
So that other one always needs 8 to be stable?
Yes. Good. Love it. Yeah. With one little exception, but we're not worrying about it right now. Okay. So check it out. When we do this, and that's actually going to happen, we're going to let this sodium, it's going to say, hey, I need stability. So either I can go and carry 7 more things over to me, or I can just carry 1 away. Which one's easier? Carrying 1 or getting rid of 1 is easier than getting 7, right? So check it out. This single electron is going to go over here. Now, if we were balanced before and we just got rid of a charge-wise, we had 11 and 11, right? We now have 11 positives and 10 negatives. This now has a charge of what? This has 11 protons and 10 electrons. After it gives it away, what's the overall charge? Positive what? Good. Which is +1. Charge. And this is going to seem super irritating, but we actually write 1 plus so that it doesn't look like we're doing math. Because it's not. I mean, we did a little bit, but it's not really math.
We write.
I would write this part. Yep. I would even draw that little line showing it move. Now, what you don't get to see if this is the only picture that we draw, because it looks like now just there's no electrons, but remember this is a real picture, so we just got rid of this whole energy level. And now we have a stable 2nd level. Okay. The sodium got rid of an electron and now has a charge of 1 positive. The chlorine just gained an electron, right? It took the 1 from sodium. So let's just do the same thing. How many protons in this chlorine?
1.
So careful.
No, protons?
Protons.
17.
17, because that was the number that we had, right? And how many electrons? We just gained another one.
18.
Do you understand where we're getting these numbers? You told me chlorine right off the beginning was what number?
7.
So notice that means it has 17 protons. And it originally had 17 electrons. If we just gained another electron, we now have 18. Okay, we haven't touched the protons at all. Here's where they're going to connect. What's this charge now? Okay. Good. We now have a charge of -1 because I have one more electron than protons. What do you know about opposites? Whether they're, like it's commonly used with people, but opposites do what to each other?
Go away.
Opposites go away?
Right.
Opposites attract. What do you think these are going to do now? If I have a positive 1 charge of sodium and a -1 charge of chlorine, are they opposite?
Yes.
So they're going to attract, right? These things come together. And we're not going to draw another picture, but underneath is where I put it in your notes. I'm just out of space. These things now come together, and we get an ionic bond. We get NaCl, which this is sodium and chlorine stuck together, which are joined by an ionic bond. It all relies on the fact that an ion is a charged atom, and now these atoms, one is positive charge, one's negative, and they stick together. This is we just made salt, is what just happened. This is table salt. Yep, sodium chloride, NaCl, this is table salt. That's all this is. And every single little salt has millions, if not billions or trillions of atoms in them that are joined just like this, every single one of them. Okay, now, anytime that you have this, it's an ionic bond. So there's a bunch of chemistry just waiting here that I'm not going to go any more into. They join. They're now stable. They're connected. They both have 8 valence electrons. Everything's nice and dandy. They're stuck together. You cannot separate these physically. You can't pull them apart. You'd have to go in and move the single electron, but we can't do that. Okay. Questions about the ionic bond? Struggling, RJ, to make sense of it?
I didn't really get to write that.
Okay, I'll wait. No, you're good.
I was just lost.
I'm more concerned. So do me a favor, interrupt me when I lose you. Okay, let's try a simpler one. Okay. So that's not going to be the one. But check this out. Couple things I just want to highlight here, and we are going to go a little bit more into the chemistry, but that's okay. How do I want to word this? Let's look at this stuff real quick. Okay, what group was sodium in? Nope, that's the number of protons.
Oh, yeah.
What group? Which column? Okay, now just hear me out here. Forget about this picture. How many valence electrons for this thing that was in group 1? Forget about this picture, we're looking at the bottom one. How many valence electrons for something in group 1? Huh. Okay, which period or row was sodium in? So that's the column, the group. What period?
It's 3 period.
Row 3, right? How many energy levels did I have to use? Huh. Okay, so let's check this one. This one's going to feel a little bit wonky.
Oh, I get it now.
What's the ones column of your group number? So it says there's a 110, right? And then how many ones to get to 17? So let me rephrase that, and I'm going to change the language, and it's just, I don't know your math language here. What's the ones digit of the number 17? 7. Okay, so check this out. Let's just go to valence. How many valence electrons did it have?
7.
So
I mean, yes,
7.
wait, how?
Group 17, there's a 7, right? There were 7 valence electrons? I added 1, right, when we did the thing? Huh. Okay, so that's pretty cool. What period is chlorine in? That's the row, the horizontal. 3, how many energy levels did I have to draw? 1? Or
3.
orbitals, rings. 1,
Oh.
2, 3. Oh, interesting.
Oh, those are called.
There's a shortcut waiting for us.
Those are called valence.
Only these ones in the outermost level. These are our valence, the most energized, the farthest away. Okay, we're gonna do one more, and if you want me to draw a picture, I can. And I lied. We're gonna do one. Oh, I'm sorry, RJ.
Wait, does it really matter where you put your electrons?
It depends on what you're proposing instead.
Because I'm confused how.
Like,
Put 2 in the inside, then.
so the first one always has 2. The good news is that you're never gonna have to draw these pictures in this class. These ones we might use a little bit, but I'm just hitting the chemistry harder because I don't know that we're gonna have chemistry next year, which means if you guys are interested in this, this is like your shot to get it. Okay, did you guys do a bunch of chemistry last year with Miss Forfietta? Well, you didn't, for sure, Fred. Okay, let's do one more. So this example is gonna have a real, I'm gonna have a hard time naming it, but let's say draw, and that's all that we're gonna instruct, okay? I want us to draw the following. I want us to show the ionic bond between, do you want it to be just as hard or a little bit harder? Let's do a little bit harder one together first. Let's do beryllium, which is number 2, and, sorry, period, group 2, it's element 4. Beryllium, it says B, and let's do that with fluorine, F. You know what? We're going to get crazy. We're going to do beryllium and bromine. So check it out. Beryllium, Be, and bromine, Br. And we're going to do the same thing that we just did a second ago, okay? Beryllium, what's its number? Number of protons?
4.
Okay. What's its group, which is its column?
2.
And the period? Which row? 2?
Yep.
Okay. I'm good with that. For bromine, it's number 35, I believe. Okay, so 35 protons. What group is beryllium? 17? What period?
4.
Okay. Before moving on, I need you guys to verify, or let me rephrase this. We're a small group and nobody's ever has a reason to be ashamed of anything. We're all learning together. How many of you could accurately tell me the protons, a group, and the period for any element that I give you? So I know you can, because you just answered this. You can look at an element and you can pick these numbers, and you see where they come from. Anybody here struggle with it? Okay. Do you have your table? You need to look at the periodic table, okay?
Yeah.
Okay. So let's check. I'm going to look at oxygen. It is element number 8. How many protons does oxygen have?
8.
8. How did you get that number?
Because of the
Because literally the number in the top left is the number of protons. Okay, so we're good with that. Which group vertically is oxygen in? It's in group 16. Love it. What period is oxygen in? 2. That's how I get these numbers. Now, beyond that, I don't want to draw the whole atom, but if I need to, it'll help. I don't want you guys to, though, for sure. So, here in a second, we're going to draw it. But we're going to try to take the shortcut first. Okay, if I have an atom that's beryllium, I'm not going to sketch all 4 protons and neutrons. All I care about is this, and I'm going to draw it big enough that I can put Be for beryllium inside of it. Here's my beryllium.
Wait, are we writing all that? Or no?
You should draw this one, yeah.
Oh.
And you should have this stuff written, and you do, which is awesome. Okay. Now, we're going to use that same thing that we did a second ago. Period 2 says it's going to have 2 energy levels if we drew the everything. It'd have 2 rings around it. But I don't care about the inner rings. I only care about the outermost right now. So I'm only going to draw 1 ring with the understanding that it's the second one, okay? So here's my second energy ring or orbital or however you want to word it. And the group number was what?
15.
Careful.
1662.
Where'd that number come from? You're still looking at oxygen, right? Okay. How about beryllium? Group 2? Now, I'm just going to go back over here for just a second. Something in group 1 had how many valence electrons?
11.
Careful.
Oh, 3.
Careful again. How many electrons in the outermost energy level?
1.
Oh, and it was group 1, right? How many valence electrons in group 17?
7.
7. Just 7.
Oh, okay.
It's just a ones digit. Okay. Which group is beryllium?
2.
So how many valence electrons should beryllium have?
2.
So I'm going to draw 2 of them. Now, RJ, if your question was where do we put the electrons? On this ring, it doesn't matter. Now, you guys don't draw this part. I'm going to add a little bit more to this picture, though. I will not do the same thing for bromine, just so you know. What you don't see, because we don't care about it right now, is there's another lower energy level that holds 2 electrons. You don't need to draw that one. I don't care if you have that or not, but know that it exists. Okay, bromine. Not a chance I'm going to do this one all the way out. How many protons?
So, in the 5, the one that'll be closest will always have 2.
Yep, the first energy level always holds 2.
Okay.
Always, always, always.
And then
Everything after that, there will be 8 valence electrons maximum. Okay. All right. So when I draw bromine, and I could be convinced to do a bigger job of this, but I don't really want to. Here's my bromine nucleus. It has all 35 of my protons. Okay. Check it out. Br. Okay. Which energy levels, energy levels, orbitals, or rings, how many would I need to use to draw the full picture? If I wanted to put every single of the 35 proton or electrons on there, I would need 4. I like where your head's at because I see what you're thinking. The period is the number of levels. I don't want to draw 35 dots to draw bromine. I'm going to skip those first 3 energy levels, and I'm only going to draw the 4th. Now beyond this, Andrew, you had the right answer, and you were close to it. If this is my 4th energy level, because it's the only one that I care about right now,
Why are we doing that?
so I just didn't dash it yet. Like that's what you're talking about, right? Okay, so I'm just not going to dash it because it saves me time. You do not need to draw 4. I don't know that I'm really going to put all 4 of them on here. But I'm going to, just so we know that they really are there. Okay. According to the fact that, what's the ones digit here? 7. So how many valence electrons, or if we reword that, how many electrons should you find in the highest energy level? 7. So I'm going to draw this last energy level. I'm going to try to draw it kind of nicely. And how many electrons go in this one? 7. So I'm going to draw those 7. Your picture, it only needs 1 circle with 7 electrons.
oh, 1 circle is 7.
Yep. Yep. Your picture could look dot and 1 circle. Now, this other part, I'm going to draw these. You don't need to. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Here's the real picture for beryllium. All 35 electrons showing. I don't need you guys to do that, but this is what it looks like. All I care about, take everything out of the first 3 rings, energy levels, orbits, and we have 7 electrons out here. Okay, first question. Stability happens when it has how many?
8.
8. Does this have 8? No. How many more does it need?
1.
This needs 1 more. Okay, we're going to keep that in mind for now. And before I move forward, RJ, did you grasp that? Because you were writing, I don't know if you caught that. This currently has 7 electrons out here.
Yeah.
Stable means it would have how many there? 7's not stable. We wrote it. Have you written down everything we have? Stability for electrons. Awesome, you know exactly. 2 or
Oh,
8. We only have 7, which means bromine needs 1 more, right? Okay. This needs 1 more electron. You see an issue coming.
Yeah.
Awesome. This has how many valence electrons? For beryllium. 2. It needs how many?
1.
Careful.
It needs.
Careful, careful, careful.
Oh, 8.
That one needs.
Because I'm in the 2nd energy level, it's definitely not a 2. It needs 6 more.
Yeah, 6
All right. So, or there's maybe a better alternative. It could either add 6 to fill up the entire 2nd row, but I could either add 6 Or I could get rid of how many? If I get rid of 1, I would have 1 valence electron, and that doesn't work. But if I get rid of 2, I'm down to the first energy level, which 2 is okay for. Okay, which is why this big picture helps. Here's the deal, though. I need beryllium. Whoa. I need to lose 2 electrons. That's what beryllium's saying. Okay. Unfortunately, in this nice little comic that we're making, oh man, I need only 1. Okay. How could we possibly make this work? And I'm going to spoil it because that's a hard question. You can't right now. You cannot make this work unless all of a sudden bromine hanging out decides, gosh, you know what? I got a twin brother who I hang out with from time to time who would love an electron as well because they want to be stable. If we had another bromine hanging out here, they each need what? How many? So let me rephrase that. Let's say we had another atom of bromine. His bro, if you will. You know what I mean? Okay. They each need 1, right? And gosh, that works really well with Mr. Beryllium, who wants to get rid of how many? 2. Oh, if we had 2 bromine and 1 beryllium, would this work out? So check it out. I'm going to redraw this picture, and I'm going to make this more comic-y. I'll call my twin. And this is going to be really cringy when I think about it later, but I kind of love the idea of just thinking about these things as like talking to each other, because it makes, they don't really, I don't think, but it makes sense. Now, if we call the twin, I'm going to draw this picture one more time, but uber simplified. We have beryllium. And I'm going to draw the picture that I imagine you guys have. Here's my outer ring that has 2. Okay, that's probably the picture you guys have. Is that true? Okay, and we want this to join in with bromine and bromine's brother bromine that have come along. And I should just done this once. And these have 7, right? 1, 2, 3, 4, 5, 6, and 7. Now, in this situation, holy consistent with my writing. Do you guys see that? I drew these 2 separately. Check that out. So consistent. Okay, if we have a second one, beryllium wants to get rid of these. Where's one of these electrons going to go?
To the top one and to the bottom.
In doing this, is beryllium now stable?
Yes.
Because it only has that first energy level. That has 2. Is this bromine stable?
Yes.
Because it has how many electrons? 8. This has 8. And then this one does have 2. And RJ, if you missed it earlier, the first energy level, every time, 2 electrons. That's stable only for that level. Okay. Well, cool. Are they all stable? Class is over, apparently. There's no homework over the weekend. All right. Later. This will be the last day that we go super hardcore into this stuff, just because it's going to turn into a chemistry class if we keep going here.
Yeah.
Okay. This makes sense. Andrew, it's clicking for you, like, super clearly.
Yeah.
Cool. Have you ever seen this before?
No.
Cool.
Maybe like a little bit, but I just never really paid attention to it and really like gone.
That's fair.
Teachers would go so fast to try to like keep up with schedule.
I'm not going slow. Just so you know, like, we just covered what was essentially 2 weeks in my chemistry class last year, just with more hand-waving magic. Yeah, my bad for keeping you guys a little late. If you're late to class,